All right, who'd like to get started? How do you find the area between two curves? And just to put the question in context, the area between two curves means you have your x and y axis. You've got one curve up here. You've got another curve down here. So how do you find the area between two curves? What would that be? And we'll just say going from A to B. So how much area is there trapped between those curves? What would the formula be? Yeah, the integral of top minus bottom. So the top curve minus the bottom curve, and dx. So in this case, it would be the integral of f of x minus g of x dx. Now, keep in mind, if you really did want to make sure that you were always getting a positive amount of area, but let's say that the curves did flip-flop at one point. Let's say that at some point f of x goes shoo-doo, and then g of x goes hoya. And now, so we started with f of x on top, with g of x on bottom, but now all of a sudden g of x is on top, and f of x is on bottom. Now we talked previously that if that happens, then this would be positive area, and that would be negative area. But what if I don't want that to be negative area? What if I really want to continue counting the total amount of area?
G of x would then be the top and x would be the bottom.
For this part.
Yes.
Yeah, for this part. So what would I have to do if I want my calculations to always give me positive area no matter what?
Absolute value.
You could do absolute value. That'd be very interesting. You could potentially do the integral of the absolute value of top minus bottom. Unfortunately, we don't know how to do absolute value. You'd think it would be easy enough.
Like a B in China thing. Like after you do the integral technique.
Oh, like are you doing the absolute value of just the top minus bottom, or are you doing the absolute value of top minus bottom dx of the whole integral?
Yes.
Well, we can automatically say this isn't right, because if you did have top minus bottom and it flip-flopped, the value of the integral would be 0, right? Potentially if the positives and the minuses cancel out, and the absolute value of 0 would still be 0. So absolute valuing the whole thing wouldn't solve the fact that the plus and minus area already canceled out. Does that make sense, Trish?
Yeah.
All right, so we'd have to do this, but that's actually trickier than it seems to absolute value a function that you're integrating. So instead, what could we do? I'll give you a hint. What could we do? If we want that to be positive area, but we also want that to be positive area.
Instead of doing the limit from A to B, you do from C.
Right, like instead of doing the whole limit from A all the way to C, in which case you'd have positive area, negative area, you do this integral first and say, okay, do this integral of f minus g, and then come over here and do this integral of g minus f. And that way they both turn out to be a positive area, and you are indeed capturing all the area. So you'd have to break up your one big integral into individual integrals every time there was a point of intersection. You'd have to start a new integral and do that integral at top or bottom. All right, so that would work. Okay, what about the volume of revolution? What's that formula? So in the volume of revolution, recall you have some sort of squiggly, and then it mirror images itself, and then it turns into some sort of nice, really nice vase that you could buy at IKEA. So what's that formula? Volume is f of x squared. Yeah, it's f of x squared, but what else? Pi f of x squared, exactly right, because this formula is literally the formula of a circle, pi r squared, where the radius is what? The actual f of x, the height of that function. Yep. So that the volume of this three-dimensional solid is just pi f of x squared, where f of x we're treating as the radius of a circle, a circular cross-section from that object. Okay, so there's your volume. And then what if we wanted the average height, which is a fun idea that perhaps you have some sort of an ant farm, or an ant farm container anyway, with liquid in it, and you want to shake it all to be perfectly level. What would that average height be? So we're going to call that the average height. What's the formula for that? Different person?
1 over b minus a.
Yeah, 1 over b minus a times the integral from a to b, just the normal f of x dx. So this is probably the nicest formula so far, because that's just the normal integral formula, and all you do is you just multiply times 1 over b minus a. Okay, so we covered quite a bit in terms of our ability to calculate areas, volumes, and average height. So then yesterday, as we were leaving, we talked about the concept of consumer surplus and producer surplus. So now let's see, I've heard from Josh, Nando, Fatima. So a few more people can speak up now. Let's look at the supply and demand curve, okay? So let's say that this is going to be my supply and demand graph. What goes on the x-axis?
Quantity?
Yep, the quantity. That's the quantity of the good that is being produced, or the quantity. Okay, what goes on the y-axis? What's that, sir? Yeah, price, or dollars, but yeah, price. The price that it's being sold at and the price that it's being purchased at. Okay, which curve always has a negative slope? Someone else? Probably. Demand, exactly. The demand curve is always a negative slope. And why is that? Because, like, let's take an example. Here's a $40 pizza, and then it goes on sale as a $30 pizza. So here was the $40 quantity demanded. We'll say 100 pizzas were demanded. But now, as a $30 pizza, because it went on sale, there's now 200 pizzas demanded. Why does the demand curve always have a negative slope? What's that, Sarah? Well, exactly, because if it's less expensive, then more people will demand it. Yeah, exactly right. Okay, so that was the demand curve. What curve is always positively sloping? Supply. And where does supply always begin? At the origin. That'd be pretty funny if it didn't start at the origin, right? So let's really understand that. Supply means, as a company, if I'm selling it for $0, how many am I willing to produce? Probably none. Unless I'm a charitable organization, right? If I'm a nice guy, I'm like, oh, I can only charge $0. I'll make 5 and give it away to some people who I think deserve it. So maybe the supply curve could start over here. But so let's just say if I'm charitable, the supply curve could start here, right? If I'm nice. Could the supply curve ever start here? What would that mean?
So the issue is going to grants increase.
Well, let's see. What would that mean? This would mean a price of $5, and yet I'm still not willing to make it. Right? So I'm like, no, forget it. That's not enough money. My supply curve, like maybe, potentially a supply curve could start up here. If what we're saying is that even at at $20, I'm like, no, forget it. I'm not going to make any. But then the idea would have to be, well, no, I think we still just say 0, 0. I don't know about that. That was an interesting thought experiment, but I think the supply curve is still starting to order. All right, so there we have our supply and demand curve. And what did we say about it? So first of all, thanks to capitalism and the invisible hand of Adam Smith and what capitalism has to offer, what is this special point called? Yeah, equilibrium. And equilibrium means everyone's happy. So if the pizza, we're just going to choose that dollar amount there and call it $32. If $32 is set, then something amazing happens, and that is that, here I'm going to call that 180. If the price is set by the society, by capitalism, by the market, if the market sets a price of $32, then by sheer happenstance and wonderful luck, the number of the supplier is willing to supply 180 pizzas, and the consumer demand is also demanding 180 pizzas. So everybody wins, right? That's a real good win-win situation. So if the capitalistic market sets the price at $32, then exactly the right number of people will show up to buy exactly the number of pizzas that were produced, so everyone's happy. Whereas, what if, let's look at 40. What if the market set the price at $40? Then what would happen? Let's look at these two. If the market was set at $40, the demand is only demanding 100 pizzas. But the supply is supplying 210 pizzas. So if we're following this $40 line across, then what does that mean? If the market sets a price of 40, we're only demanding 100, but they made 210. You got a bunch of extra pizzas that, unless you have a freezer and you can freeze it and the pizza's so good, you probably just threw all those pizzas away. And as a company, you're very, very sad because you had a lot of waste. Your employees are probably like, we're going to throw it away anyway. Why can't I take it home? Because most companies have rules that if there's extra food at the end of the night, are you allowed to take it home and eat it? No, you have to throw it away, don't you? Isn't it just awful? Some companies are nice enough that they take that food and they give it to a charitable organization. And then again, the employees are like, I'm a charitable organization. But no. Okay, so then what if the market set a price, well, if just for whatever reason, the price was only being charged for 20 bucks, then what would happen? Here, the supply is only supplying 100, but the demand is demanding 210, so then what does that mean? If the suppliers only made 100, but 210 people showed up. Yeah, not everybody gets it, and they're gonna have a lot of unhappy people like, man, you guys never have enough pizza, you're always running out. So that business would get a bad rap. Okay, well that's just one way to look at it. Now that I've thoroughly messed up my graph, start over here. That's not what we were talking about. We were talking about consumer surplus and producer surplus. So once again, let's say that this is our fixed equilibrium price, okay? Then consider this person, okay? Consider the person right there, the 70th person who was willing to buy this product. That's what we want to think about. This person right here, that person, up on the demand curve, they were willing to pay, so I'm going to go up here, the 70th person. The 70th person was willing to pay 50 bucks. But the equilibrium price was only 32 bucks. So what does that mean for that person? I was willing to spend 50, but I only had to pay 32. That's great. I have 18 extra dollars in my pocket. So the 70th person has 18 extra dollars in my pocket. So does the 69th person. They have extra money in their pocket. So does the 60th person. So does the 50th person. In fact, all the persons to the left of the equilibrium point all have extra money in their pocket. How much extra money? The difference between what they would have paid and the equilibrium price. So this difference right here, for every single person that we're talking about, represents the amount of extra money that they have in their pocket. And therefore, if you find the area of this shaded triangle, that will represent all the extra money in consumers' pockets. In consumers' pockets. And therefore, we call it consumer surplus. Not very good. Isn't the supply and demand curve interesting? I mean, you could go on and on about this thing. Talk about if you're out on a first date and you're like, I don't know what to talk about. You want to talk about supply and demand? Okay, now what about the producer? So let's consider the 70th product produced by the producer. They were willing to sell it for 10 bucks, right? Because now this is the supply curve. I should write that back down there, supply. So this 70th product produced by the supplier, they would have sold it for 10 bucks. But because the capitalistic market thinks capitalism set the price at $32, they now just made what? They were going to sell it for 10, but they got to make 32. They just made 22 extra bucks. So they made $22 of extra profit that they don't have to give to their employees. I'm kidding. I'm sure they'll share it with their employees. But they got $22 of extra product. And in fact, the 60th product, that producer also made extra money. And all of these products to the left here all made that business extra money because there were people, because they would have been willing to sell it for less. Yeah. So then all that money is called what? The producer surplus. Wow, there really is a lot to consider, right? Like when I was looking at this vertical stripe, we're looking at producer surplus and consumer surplus. But when I was looking at the horizontal stripe, we were looking at having too much inventory or not enough inventory. And then we haven't even talked about the fact that the whole supply curve could move up or down, or that the whole demand curve could move up or down. That's like a whole other consideration. What if demand of the society actually changed? Like what if the whole society was like, we're going to go on a diet, try not to eat as much pizza. Well, then the whole graph changes, right? Okay, so here we have it. I think I have a joke for you. I don't think I told you. Uh-oh. There we go. Did I tell you the janitor joke?
Yes.
Oh, man. Did I tell you the jelly joke? Okay, good. This one's very clever. Have you ever eaten just the jelly from inside a jelly donut? It's filling. All right. So today is what then? Today is the 18th?
Yes.
Yeah, so we get to start 3-7 today and then finish it next Monday. We already started 3-7, so we're really having a lot of good amount of time here at the end that we could even look at the practice test before your real test. So who knows, we might finish 3-7 today. And then next week we could devote Tuesday to preparing for the test and the Thursday is your actual test. Yep. All right, well let's go ahead and get started. So 3,7, we've already talked about this graph now, but now let's really look at it and see what we're interested in finding. We're interested in finding the blue area, and we're interested in finding the pink area. Now, the blue area for sure is a triangle, and as a triangle, I can calculate that area pretty easily by doing 1/2 base times height. It's just a triangle. The pink area is not a triangle. I can approximate it with a triangle, but I would really need an integral, right? So the integral that we'll do for consumer surplus is going to be top minus bottom, where the bottom is strictly a horizontal line. And then to calculate the area of the pink, we'll again do top minus bottom, where the top is a horizontal line. So that's what we're looking at. Notice that they call the equilibrium point P star Q star. So we're going to keep that notation. We'll call it P star Q star. Concerned, the demand curve, okay, is P equal D of Q. Let's wrap our minds around that. First of all, the demand curve, it says P equals. So what is this function equaling? So price. Because after all, what's the y-axis? Price. Like if that was the y-axis, it would be y equals something of x. But this is the price axis, so it's P equals, and D represents demand, and Q is the input variable, right? So the demand curve says, if you tell me how many items are being demanded, then I'll tell you the price that they're willing to pay. So that's the demand curve. Likewise up here, it's still P equals because our axis is P, just like it would be the y-axis, y equals, so it's P equals. And again, S represents supply. So now again, if you tell me the number of products you're willing to supply, then that's the price they're willing to sell it for. Everyone feel okay about that? Those are all the definitions. Okay, so we have these formulas. We might as well write them down nice and neat, somewhere on your paper. You've got a lot of room up there, maybe up in the right-hand corner. So I'm going to go ahead and write down nice and big here. Given a demand function and a supply function at an equilibrium point. So I'm just going to always write CS for consumer surplus and PS for producer surplus. My consumer surplus is the integral from 0 to Q star. Now, stop. Why does that make sense? We're going the integral from 0 to Q star. Why is my integral going from 0 to Q star? Because that's where the consumer surplus is. No, that's where the area is. Okay, so that makes sense. We're doing our integral from zero products consumed or demanded up to Q star products demanded and supplied. So we're going from 0 to Q star. And again, we want to find, we're doing the blue area right now. This is going to be the top curve minus the bottom curve. So let's see how that works. The top curve is the demand curve. So we're going to write D of Q. And the bottom curve, okay, is a horizontal straight line. Who remembers the formula for a horizontal straight line? That's correct. The formula for a horizontal straight line is always y equals the y-intercept. And that's the formula for a horizontal straight line. So if the y-intercept has to be P star. So the formula we're looking at is P star. And so therefore, this is the top. I'm going to write it in. D of Q is the top curve minus the bottom curve, which is simply P star. And then that would be DQ. Now notice that what I just wrote down is different from what's on the paper. Because I started by writing down, from our understanding, the area between two curves is top minus bottom. So we're going to derive the formula ourselves here. I didn't write down what's on the board. I'm writing down our conceptual understanding of how you find the blue area, which is an integral of the top curve minus the bottom curve. Now we'll go ahead and take this integral, and we'll take the integral by splitting it up into two different integrals being subtracted. So it'd be the integral of 0 to Q star of D of Q dq. Oh, look how confusing that potentially is. Minus the integral from 0 to Q star of P star dq. All we did there is just break the integral up over subtraction. Honestly, look at that. It's like I just saw that for the first time. D of Q dq One of those at Dairy Queen. What does this DQ represent? The demand function. What does that DQ represent? Yeah, the infinitely thin width of one rectangle in the Riemann sum, right? So that's pretty funny. Okay, now this one we actually have to do. So there's nothing to be done there. That's just the integral that we have to calculate depending on the demand curve that they give us. But this, we can go ahead and find out. P star is just a number. P star is just a number. Let me ask you, if I was going to do the integral of just a number, like 5, what would the answer be? It would just be 5x, right? The antiderivative of 5 would just be 5x. Now we're going from 0 to q star. So with my example here, if I took the antiderivative first, it would be 5x, and we'd be integrating from 0 to q star. And then I would do the fundamental theorem of calculus, and it'd be something minus something. And that would be 5 times q star minus 5 times 0. Well, what's 5 times 0? Nothing. And the answer would just be 5 times q star. In our case, the number is p star. So what's the answer to this integral? Yeah, p star, q star. That's our actual formula. And that is what's written down on the page. It's what's in your textbook. And I just wanted you to at least see that this formula didn't pop out of nowhere, an angel coming down, handing it to us. It just came directly from finding the area between two curves, top minus bottom, which we are all perfectly capable of doing that integral ourselves and deriving that formula. You're like, you don't have to do the formula, I'll derive the formula myself. So definitely that formula now, we want to circle it real good and keep it with us for the rest of the session. Now, let's derive the formula for producer surplus. Producer surplus, we would derive it in the same way. We would say, I'm going to do top minus bottom. So my integral again from 0 to q star, where once again we're going to do top minus bottom. And what's the top this time? What's the top of the pink p star? Yeah, that's p star. Here, that's p star. That's q star. So now the top curve is simply the number p star minus the bottom, which is the supply curve, which is S of Q. So again, we're doing the integral of the subtraction problem, so you can turn that into the subtraction problem of two integrals. So my first integral would be 0 to q star, p star, dq. Oh, I forgot my dq again. Minus the integral of 0 to q star of S of Q. And then likewise, this integral simply comes out as the product of p star times q star. So just like this one, the integral of p star dq became p star qq, or sorry, p star q star. And then here, this one, the integral of p star dq will become p star q star. We can do all the work, but it's going to be the same result. So p star q star minus this. And so that is producer surplus. Now, folks, almost always in mathematics, and this is what makes math so clever. Anyway, anytime you can prove something one way, you can prove it another way. So now I want you to notice, what is this p star q star anyway? What is that? What is the product of p star times q star? What is it on the graph? Here's q star. Underneath it. So here's the point, q star. And here's the point, p star. So what does that even mean to multiply p star times q star? What is it telling me? Well, that's true. It would be revenue. Price times quantity is revenue. And it's also telling us area, because look, p star, that's how high this is. And that's how wide this is. So area is base times height. This whole rectangle right here, the area of that thing is p star q star. So what does p star q star represent? The area of that rectangle. So, oh, darn it. I want you to see the blue Pardon, I just moving this board up and down. Okay, there. I'll be back. So this whole rectangle right here, the area of that rectangle is P star Q star. That's an area. So once again, what if you wanted to know the area of the blue curve only? If you wanted to just know the blue area, you could take the integral of the whole blue curve. So just take the integral of the blue of this curve and find the whole area, right? The whole darn thing. Find the whole area underneath the demand curve. So that'd be 0 to Q star of the demand curve. But if I only wanted the part in blue, what would I subtract off? Yeah, that thing. And look, that's the formula right there again. So the consumer surplus is simply the integral of the demand curve minusing that rectangle. And that's the formula we got. So now on the other hand, what if I wanted just the pink area? If I just wanted the pink area, well, first of all, I could take the area of the whole rectangle, right? The whole rectangle contains the pink area, but what would I have to subtract out? This area. And what's the white area? Under the supply curve. So we just subtract out the integral of the supply curve. And is that the area? Or, is that the formula we got? Yeah. So that's two completely different ways to derive the exact same formulas. And depending on which way you want to think about it, that's how you can try to memorize the formula. All right, so we have our formula. We're ready to go. We have a good, strong understanding of what all this business is all about. So now we can go ahead and try a couple problems. What is it we're going to try to calculate? We're going to calculate the consumer surplus, find the consumer surplus, and we're going to calculate the producer surplus. So at the end of the day, we're given a particular demand curve and a particular supply curve, and we're being asked to calculate how much money do consumers still have in their pocket because they paid less than what they were willing to pay, and how much money did the business make because they earned more money than they were willing to earn. Okay, everybody ready? Yes, great. That's very tall. Let's say, number one, given, oh good, we're working in X, not Q. Given X number of items, the demand function is that, and the supply function is that. So first things first, just find the equilibrium quantity. So everybody take a look. We're going to make a graph. In fact, maybe I'm going to go over here and make, well, it doesn't matter where I make my graph. I'm going to go to the far right-hand side. Let's make a graph. What does my demand function look like? You might want to write it backwards. It's negative 1/2 X plus 300. Why did I write it backwards? Yeah, typically it's mx plus b. So I just rewrote it as mx plus b. So I'm going to go ahead and go up here to my y-intercept at 300. And then it's going down one right too. I don't really have to worry too much about being exact on this. I'm just going to draw a negative slope. So there's my demand curve, d of x. And now I need my supply curve. You'll notice, in this case, where's the y-intercept? Yeah, they put the y-intercept at 0, so it starts at the origin. And then the slope is positive. I'm just going to draw a positive slope. Because now I can very clearly see my point of intersection, which is giving me my Q star and my P star. So now how do we find that point of intersection? How do you find any point of intersection? Yeah, now why is it that you just set the functions equal to each other? Why is it that by setting the function equal to each other, you're finding the point of intersection?
So there's going to be that one spot where the x and y are 5%, so if you find the x to
Okay, that's a really nice way of saying it, Josh. The point of intersection means x and y are the same for both functions, and since that represents the y, you're setting the y equal to each other, and then you're finding the resulting x that makes that y equal to each other. Another way we can think of it is, what does the function represent always? Since the beginning of the semester, the function represents the height. And a point of intersection means they have the same height. Okay, so now that we all have this memorized, that to find a point of intersection, I'm going to write it down once. To find a point of intersection set d of x equal to s of x. Right, so that's when, and then a third way of thinking about it, what are we saying about our supply and demand curves? Demand is equal to supply. That'll be our equilibrium point when the demand is equal to supply. So I'm going to write down 0.3x equals 300 minus 0.5x, and then move the 0.5x over. Now keep in mind, this is pretty trivial algebra, isn't it? A nice little relief. So then dividing by 0.8, times 0.8 going to 300. 375? Oh, all right. So 375 is my Q star. Therefore, what is the P star? Or what is the supply and the demand? What price? How do I find out? Plug it. Yeah, plug it into either of them, right? Because they should theoretically be the same. So I'm going to plug it into the easier one. So I'm going to do S of 375, which is 0.3 times 375, which is something. Anybody got it? 112.5. Okay. So that is our P star. 112.5. There we go. Now, because the supply and demand curves are linear, this is a problem that we can now finish using geometry only. We don't have to do any calculus at all. I can just go ahead and split, go ahead and draw your horizontal line. And I can just go ahead and find the area of this triangle. Right? What's the width of the triangle? How wide is the triangle? 375. And then how tall is the triangle? 112 to 300. So that's a difference of 187.5, is it? Yeah. Yeah. So I can just find the area of that triangle pretty easily. That area is 1/2 base times height. Likewise, I can go ahead and find the area of my producer surplus, because that triangle is also, so the base is still 375 and the height is 112.5. So that was easy. So that area is going to be 1/2 base times height. So I just want you to notice that there's oftentimes many ways to solve a problem. And even though they are asking us to find the consumer surplus and the producer surplus using calculus, in this case, the functions are linear, so we can find these results without doing calculus, which is a nice way of checking our answer. Did anyone else get a consumer surplus of 35,156 and a producer surplus of $21,093.75? Okay. Is that real money? Is this money real? Is it really in the consumer's pockets, and is it really in the business's bank accounts? Yeah, I mean, kind of, you know. Oh, but is it really real? I mean, the business, you know, so I'm a business, and I sold it for 40, even though I was willing to sell it for 10. So all I'm really talking about is that there's a certain amount of money, a differential that's in my bank account right now that I'm glad I have, right? So I mean, is it real money or is it just money I'm glad I have? I mean, I don't know. It's an interesting question. Henry?
So there is like the example we did with pizzas this morning. They got more producer surplus than consumer surplus.
Well, that's true. Yeah, apparently the consumers got more money in their pocket than the producers did.
But if it was switched, like why wouldn't they sell it for less? Or sell it, yeah.
Well, essentially what we're saying is we are all victim of capitalism's equilibrium point. we don't get to just choose whatever price we want. We have to go with the price set by the market. If you do choose a price other than what the market says, you'd be leaving the equilibrium point and you'd have inventory surplus or you'd run out.
Yeah, but is it really that bad?
Yeah, I mean, not necessarily. Like I said, Pizza Bianca was this fancy pizza place where you got to wait in line for 2 hours. I remember one time we went there to get in line, we're like, forget it, we'll go somewhere else. That doesn't mean I hate them. You know, like, we just didn't go to dinner there that night. Yeah, so is it that bad? Probably not. Is it that bad to have extra inventory on your shelves? None of it doesn't go bad. I mean, if you just have to wait till tomorrow, then you can sell it. Right? These are all interesting questions. Okay, so now let's do the calculus. So here's our calculus. The calculus should not be too bad. I've got the bar here, so I'm just going to do it down here. So consumer surplus, the first thing I'm going to do is write down the formula. So always write down the formula first. So 0 to Q star of the demand curve minus P star Q star. Now notice the formula is kind of easy to remember because for consumer surplus, I'm going to do the demand curve minus the rectangle, whereas for producer surplus, I'm going to do the rectangle minus the supply curve. So that makes sense that the producer surplus is going to be the integral of the supply curve, and the consumer surplus is going to be the integral of the demand curve. Okay, so now we're going to do our integral from 0 to 375 of the demand curve, which is 300 minus 0.5x first, x, and then minus the P star Q star is just going to be two numbers. I should write for an order. Times 375. Did I do that right? Notice we got to be kind of flexible with changing things from Q over to X or X over to Q. Because sometimes problems have you do it in X, and sometimes problems, like they gave us the formula in terms of Q, but then they gave us the problems to do in terms of X, and you know, we just have to be flexible in that regard. Okay, so in finishing this problem, this is simply a number, whereas this we have to do the integral. So the integral of 300 is, or the antiderivative of 300 is 300x, and the integral of 1/2 x to the 1. Well, I'm going to make that a fraction instead. Instead of 1.5, I'm going to put 1/2 because that makes it easier for me to divide. So I add 1, so it's x squared. And then what's 1/2 divided by 2? 1/2 divided by 2 would be 1/2 times 1/2, which is 1/4. So that gives us minus 1/4. And that's going to be from 0 to 375 minus 112 times 375, which is 42,187.5. Now you notice that this integral is not very hard. And why is that? Yeah, because the demand and supply function were pretty simple. You know? Real supply and demand functions as models in the real world are not going to be linear. Linear is like the least sophisticated possible model you can get. When people actually try to do supply and demand curves, they're pretty complex. Okay, so now this is going to be the fundamental theorem of calculus minus 42,187.5. So here I would have, I'll write that much bigger. So I'd have parenthesis, minus that. So this is 300 something minus 1/4 something squared minus, oh, I like plugging in 0. What happens when I plug 0 and all that? Yeah, that's just 0. So I'm not going to bother writing that structure down. Boy, I'm going to lose that calculator. By that I mean I'm going to kill it. Let's take. So now that's going to be 300 times 375 minus 0.25, 375 squared. So that becomes 77,343 times 42,187. Look at the size of the numbers involved. I bet right now you're thinking, gosh, geometry is the way to go for this one. Because the geometry wasn't all that bad, it was just two triangles. But that's only because our supply and demand curve was so unsophisticated. And our answer is 35,156.5. Yeah, I think I'm liking this idea of calling consumer surplus not money I didn't have to spend, but money I'm glad I didn't spend. That's really what it is. It's just, I got money in my pocket, I'm glad I didn't have to spend. That's what consumer surplus is. Did we get the same answer? Yeah. Okay, so then producer surplus. So producer surplus is going to be the rectangle minus the integral of the supply curve. So the rectangle we already found. Notice that now that we have some calculations over there, we can probably cheat a little bit and just say, well, my P star Q star was 42,185. Sorry, 42,187.5 minus my integral from 0 to 375 of my supply curve, which is 0.3 x to the 1. Do you think I'm cheating by just writing down 42,000 directly? No. It really just depends on if you, your brain, and your audience can all see what you just did. Someone in the audience might be like, well, and then you have to go like, look at the last problem I did. It just did P star Q star. So antiderivative of 0.3x to the first. Now again, what if we rewrite 0.3 as 3/10? Does that allow us to do the computation a little easier? What's 3/10 divided by 2? It's 3/10 times 1/2, right? So when I do my antiderivative, it'd be x squared, and then 3, is that 3/20? Yeah, so 3/20 from 0 to 375. I'm probably going to put that whole thing in a bracket. All right, so we have 42,187 minus, and again, this is going to be, oh, now watch, we're doing minusing the fundamental theorem of calculus. So I would need to put an extra set of brackets there to make sure that I'm subtracting the fundamental theorem of calculus, right? Because the fundamental theorem of calculus is something minus something. So I have to put brackets on the whole thing so I make sure I distribute. Which doesn't matter at all, right? Because what happens when I plug in 0? It's just 0. But it's good to be thinking about these things. There. So yeah, 42,187.5 minus whatever that is. Which is so the producer surplus is $21,000 of money I'm glad I made. Folks, can I ask you a personal question? When you do, I mean, this is not that personal, it's just not a computation. When you do 3/20 times 375 squared, do you type in all at once 3 divided by 20 times 375 squared? Or do you, have you ever tried this, 3 divided by 20, enter, times 375 squared? Do you ever hit an enter in between computations? Oh, okay, even better. You do the 375 squared and then enter? You hit enter, and then you do times 3 divided by 20? Okay, perfect. Yeah, you can do that. A really good way to chunk up a computation is just to throw an enter in the middle of it. So like you can do 3 divided by 20, enter, and then times 375 squared. And then you know you're getting it right. See, the biggest problem is, and this is a big problem, I see a lot of people do 3 divided by 20 times 375 squared, which, to be honest, your calculator will do that correctly. So this is not the best example. The calculator actually did that right. But sometimes, like 3 divided by 10 squared, did they mean 3/10 squared, or did they mean 3 over 10 squared? And see, in this particular case, your calculator did that one, not this one. So it's just so important that you're either hitting an enter sign in between a long computation, or you're using parentheses to tell your calculator what to do. So you'd either be 3 divided by 10 squared, or you'd be 3/10 squared. Parentheses are so important. Yeah?
Does it say like all the digits? Or does it say it's the calculator?
It'll show as many digits as the calculator can keep. But that's a really good question. How would you do an experiment?
Split it up.
What?
Split it up. Is it all
It's good.
of them? Is it like that? So,
Yeah, that's a good point. I suppose you might lose some digits there.
or
Yeah. Huh. That's a good question, Henry. I'm not sure. Because like when you do a computation, like I'll just do 1 divided by 7. That was not 1 divided by 7. See, I only see what? 2, 4, 6, 8, 10 digits. But if I now did a computation, would it give me more than 10 digits? So I can test this hypothesis. I'm going to multiply by 1 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. If it didn't keep any more digits, then by multiplying by 1 billion, it's just going to give me a whole number. Whereas, it did actually. All it did was move the decimal. See, it should know better that 1/7 continues forever. And it should have moved the decimal and then continued to give me 1, 4, 2, 8, 5, 7. But it didn't. So Henry, there's an experiment. Then tested your hypothesis. All right, folks, let's try another one. That one was simple because the curves were linear. So let's try some where the curves are not linear. I'm going to erase all my derivations now and just keep the formula. It's a little messy up there. Okay, oh good. So this next one is a quadratic. So that's a little more tricky. We certainly can't test this one using geometry. All right. Okay. So what do we do first? Consider circle. Minus a rectangle. Whereas the producer surplus is the rectangle minus supply curve. Okay, we should just take a break. What the heck? My phone just went off, might as well. So times 11:50, let's be back at 12. Anyway, I'm incredibly disappointed by my calculator.
because it only shows the same number of digits anyway, so if it was still in there, I would know.
Yeah.
Yeah, I know.
And I know my calculator is capable of so much more because if I had typed in, what if I actually typed it all in at once? 1/7 times a billion. That's really the test. So if I do 1/7 times 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope, it still only gives me the 1 digit. Okay, the experiment meant
Because it
nothing.
only shows you that. So you'd have to find a terminating decimal that factor, say 4, but then that is 1/16. That's just going to show us. I mean, especially when we're doing whatever it's called. Theorem of calculus.
Fundamental calculus?
Yeah. You try to put both sides in at the same time, you have like 17 parentheses.
Yeah. Yeah, that's a lot of parentheses, isn't it?
But on the second one, sometimes you have to.
Yeah.
You want to keep all the. That's
If you want to keep all the accuracy. Yeah. Yeah, quite a conundrum, isn't it? All because we desire accuracy. Whatever that is.
I watched a video on 42 yesterday.
Huh?
Cool number.
Mm-hmm. Oh, does it actually have cool properties?
Yeah, it's like, let's see what they say. It says, if you take like the prime factorization,
Mm-hmm.
the inverse of the numbers of the prime factorization and you subtract the inverse of 42,
Mm-hmm.
you get 1. So that's like some special name. Then there's one that's like, if it's multiplied by like 6 and 7 multiplied to get 42.
Mm-hmm.
So like if 2 or 3 is multiplied, so 6 is also in this category, and then 5 and 4 are 20 would be in the category. It's like called pair or something.
I don't know that one, but they could be called triangular numbers.
So
Oh wait, no.
yeah, but they're talking like Douglas Adams, I guess, wrote the Hitchhiker's Guide, and so they said that it was even a big deal before that.
Wow, I had no idea.
Oh yeah, and then that Mario thing that I sent you, so you can put in whatever function you want.
Mm-hmm.
You could even put in like a piecewise and just make them do like a weird.
Oh, that's very fun. I had no idea that.
Yeah, Vsauce did that. It's ridiculous.
Good old Vsauce. Having a good time.
Yeah, I watched a video on why he doesn't really post anymore. It's sad.
Oh, why doesn't he?
He's touring with the guy from Mythbusters.
Yeah.
So I think he has the equipment or time.
Oh, that makes sense.
We gotta go see Vsauce live.
You did?
If I do.
Oh, that'd be fun. Okay.
Mister, would you miss your
Mister?
Yeah, Mister.
Are you talking to me?
G, yeah.
Oh, okay. Hi, Sarah.
Would you miss your graduation for a final exam?
Would I miss my graduation?
For a final exam, yes.
I don't understand. Would I miss seeing your graduation?
No, would you miss your own graduation because you have a final exam for that exam?
That shouldn't happen. All teachers are told that they're supposed to reschedule their final exams to not interfere with graduation. So what class is it?
I have like May 9, I have
They should change that. You should go.
Still, the same graduation is that.
Yeah, no, that shouldn't happen. All finals on Thursday should be rescheduled to another day.
Maybe I hope so. Because
Well,
last
just-
semester, I remember they changed it. I don't know.
Yeah, just bring it up with your teacher. They'll change it. Yeah. Tell me who the teacher is and I'll change it for you.
Her name is Alison.
Who is it?
Alison, I don't know.
I can't hear you.
Alison something.
Well, let me know what their name is and I'll go address it with them.
I don't know.
Our finals on the 7th, so they expect us to have all our grades in by
Hmm?
the day after.
Yeah, you got to be real fast for seniors.
All right, folks. Let's try the next couple. And just to see where we're going, we have a few of these to try. So we have this one, which is quadratic, the next one, which is a root, and then we have a totally different type, which is linear. Oh, and then we still also have some other types of problems to do, namely continuous income stream, and that's it. Okay. So we want to finish up these, and then try one more problem type. So I might just help you get these set up, because everyone can now finish the integral once we get it set up. So let's take this next one. Oops. Take a look at the next one. So number 5, it says, we have a supply and demand function, which is quadratic. So let's start by making a graph. My demand curve is an upside down parabola with y-intercept of 504. So, by the way, we can tell from this that the vertex is actually on the y-intercept. So the demand curve looks something like that. So the top of the parabola is the part that touches. It's not like it's over here going like this. Because once again, can a demand curve ever go up? No, it can only strictly go down. So this parabola starts up here at 504, and then it starts heading down. And then we also have a positive parabola, which also starts at the origin. So it's strictly speaking going like this. And we end up with some sort of point of intersection over here. Now, obviously, it's not important to show the left-hand side of either of those parabolae. The left-hand side is meaningless, because you can't sell a negative quantity of good. I just wanted to make sure we all knew that that was the bottom of this parabola and that was the top of that parabola. So there's our point of intersection. How do we find it? So, yeah, just set them equal to each other. So here's my, here we go. What's the most efficient thing to do? Should I set d of x equal to s of x or s of x equal to d of x? Yeah, I suppose it really doesn't matter, but you want to smooth things as least amount of times as possible. So I typically want my x on the left and my number on the right. And since this one has a number, 504, I'm going to put that one on the right so that the number is already on the right. And then I'll put the 0.4x squared on the left. And so now to solve this, all I do is just move the 0.2x squared over to the left. Okay, so we have 0.6x squared equals 504.6. Dividing off of 0.6. We have x squared equals some large number. Oh, 841. There we go. And that's just x squared, so we still have to square root. I get x equals the square root of that, which I don't know. 29. So that means Q star is 29. And then how do we find P star? Now plug it into the easiest one, which would be S of X. So S of 29 is 0.4 times 29 squared, which is 336.4. You'll notice from the context of this problem, do you think that this problem represents a real situation? Because it says right now that we're selling 29 items, and the cost is $336. Huh? Yeah, isn't that 841 right there? But then you square root it and you get 29. I didn't do that computation. I trusted whoever told me. 504.6. Yeah, I got 841. What's your question, sir? No, really, what's your question? Yeah, it's 841. X squared equals 841. Oh, because you did divide by 6. It's divided by 0.6. That's 0.6. Yeah. Yeah, I mean, if we're only selling 29 things for $336,
Then you can switch food.
yeah, I mean, hopefully that's not for the whole year, because that's only $9,700. So maybe that's per week. You know, maybe that makes more sense that that's what we're talking about. Okay. Yeah, probably so. A week, or maybe even in a day. You know, that'd be even better. Maybe even in an hour. No, probably just a day or a week. Okay, so now find the consumer surplus. Oh, we're not done. No, yeah, we are done. So it's 29 items at $336.40. So now we find consumer surplus and producer surplus. And here I think we could probably just leave the integrals for you to do on your own. So the consumer surplus is the integral from 0 to Q star of the demand curve, Q, minus P star Q star. I'm just going to set it up with you. So that's from 0 to 29 of the demand curve, which is 504.6 minus 0.2x squared dx, minus our rectangular area, which is 336.4 times 29. Folks, do you notice how I just wrapped the integrand in parentheses? Never used that word before. The thing in the integral is the integrand, just like the thing inside the radical is the radicand. So I wrapped my integrand within parentheses because if you were to do this on Desmos, you would probably need to have parentheses on the integrand for it to interpret it correctly. So where are we at now with the subtitle for this class? It's Advanced Techniques for Algebraic Manipulation and Simplification and Window Sizing and Parenthesis Use. All right, these are all the things we're learning. All right, and all of those things are bonus. I'm not even charging you more for those extra things. All right, so then doing our integral, it would just be what? 504.6x minus, add 1, divide by. So this is really 2/10, right? I'm going to change my 0.2 into 2/10 because that way when I add 1 to get 3, I can easily divide by 3 because dividing by 3, this just becomes 2/30. Let me know if that doesn't make sense to you because I'd really like you to be able to do that. Instead of 0.2, make it 2/10 because when you add 1 to make it 3, dividing by 3 means you just multiply the denominator by 3. And that's a very handy way to think about it. So we have that from 0 to 29. And then minusing the 336.4 minus 975.6. But you can go ahead and wrap that one out, or you can finish it up. Yes, sir. Sorry, that's a mess. I'm plugging it into either of the functions. You can plug it into S of x or d of x, but I chose S of x because the formula is easier. bet you all noticed how excited you were that you're plugging in 0. Hey, are we always plugging in 0? Yeah, because the formula itself, the integral always goes from 0. So that's real nice. We're only ever doing part of the fundamental theorem of calculus. So we'd have 1.6 times 29 minus 2/30 29 cubed minus 9755.6. Did anyone else get 3,251.86 repeating? All right. So that was the consumer surplus. And again, that's just money that we're glad we didn't spend. So then the producer surplus would be P star Q star, which we already know, minus the integral of the supply curve, which we already know P star Q star is 975.6. So, and that's going to be the integral from 0 to 29 of 0.4 x squared x. All right, folks, can we just write that down and move on? You can always go back and do that second computation, but it's essentially just like the first computation. You'll finish the integral, and then you have both of your quantities. We'd like to go ahead and set up this next one, which is a really interesting square root problem, and the next one, and then move on to the last subject. So go ahead and set up that user server number 1. What's that, Josh? There are. So in this next problem, we can assume that the demand curve goes down and the supply curve goes up. But do you suppose we should look at what the graph actually looks like before we just go drawing a line? I mean, it's fair to assume that the demand curve has to go down, but it wouldn't hurt for us to actually know what that graph looks like. Oh, and there we go. That's what that looks like. Now, this is interesting to note because where's the y-intercept? Is there a y-intercept? Yeah, it's an asymptote. That's interesting and problematic. Or is it problematic? I don't know, but there's an asymptote. So what does that mean for the demand curve? As the number, so
There will always be someone willing to pay some amount.
yeah, I mean, just really imagine, like, if there was just one person demanding it, there's one person willing to spend essentially infinite amount of money for this item. Or, you know, to buy even a part of it. Like if this was something you could buy part of, like a pizza. Like, well, I can't afford the whole pizza, but I'll buy one part of a slice. There would be someone who's willing to pay almost an infinite amount of money for it. So I don't know what that means or you know, why this particular demand curve was chosen. But the demand curve must match the data they received from the marketing data they did on what people were willing to pay and how many they were willing to buy. Yeah, so maybe when someone uses a demand function like this, they should say this is only valid for x bigger than 10, right? Because then the rest of the curve does a good job of matching it, but it would be nonsense to consider 1, x equals 1. Okay, so that's what that curve looks like, and then 2 square root of x, oops, oh, 2 square root of x looks like that. So in terms of window resizing, I want to make my x-axis go out much further, maybe 2,000. There, that looks much better. So that's what our 2 curves look like, folks. Once again, the supply curve starts at the origin, goes up. The demand curve comes down asymptotically from infinity, and they cross at, hey, look, we can just kind of cheat and look. It intersects at 841.58. We're still going to do the math because the math is interesting. But that's what your graph should look like. So everyone go ahead and draw the graph. So let's see here. Our graph was a square root function, which looks like that, and an asymptote from heaven, which looks like that. And what was it? 841 and what else? 58? Okay. So there's our graph so far. We still need to prove it. That is by setting the two equal to each other. So now how is this going to work out? If I set d of x, no, s of x equal to d of x. So we have 2 root x equals 1682 over root x. I want you to appreciate that this looks like a hard problem, doesn't it?
No.
Oh, it doesn't, Josh?
No.
I could ask a lot of other people who disagree with you. At face value, just looking at it, it might look so hard that you would actually not approach it. You'd say, I'll do this later, and then you never do it. Right? I'm making a metaphor for all of human life right now.
Yeah.
Sometimes a problem looks hard and you avoid it, and you avoid it, and you avoid it, and you put off a particular part of your life for years. Right? I mean, this is what happens. There are certain things in life that we avoid. And then you finally go to do it, and you're like, oh my gosh, that was so easy. Why didn't I do that 18 years ago? So how do I solve for x?
You multiply by square root of x.
Yeah, I've got a denominator, and the way you get rid of a denominator is multiplying by the denominator. And so that cancels out. And then, yeah, 2 root x times root x is 2 root x squared. That cancels out, and that's just 2x equals 1682. See, like now, really, truly, that's a metaphor for life. You finally approach the thing that you've been avoiding in your life, and you're like, oh my gosh, it's 2x. And it's so easy, just divide by 2.
Is that another sub-branch for?
Yeah, that's part of the subtitle of the course. Realizing that you put off part of your life for far too long, you should just go do it. Okay, so that's 841. So now, JR, what function do you want to plug that back into? D of x or s of x? Yeah, s of x seems much better because it's simpler. S of x is 2 root x. So I'm going to plug in 841, which we saw in a previous problem, that's 29. Well, the square root of 841 is 29. So that's 2 times 29, which is, hey, what do you know, 58. Okay, so we fully justified the work. So now we're allowed to have looked at Desmos and seen that the coordinate was 841.58. And I'm just going to help you start up the integral. So we're going from 0 to 841. And the demand curve, how are we going to have to rewrite 1682 over root x?
1682.
Right. Yeah, we know that in order to integrate that square root, first of all, it can't be a square root, it has to be x to the power of 1/2. And it can't be in the denominator, it has to be in the numerator, so it's going to be a negative x to the 1/2. So we have the integral of 0 to 841 of 1682 x to the negative 1/2 dx minus whatever that is. So when you do the antiderivative and you add 1 to negative 1/2, that's really adding 2 halves. So you get x to the 1/2. And then what's 1682 divided by 1/2? 1682 divided by 1/2. Yeah, that's really, dividing by 1/2 is really multiplying by the reciprocal 2 over 1. So then it'd be, what did you say? Yeah, 3364. So now we have 3364 x to the 1/2 from 0 to 841 minus that. And so that's just 3364, the square root of 841 minus 467. Did anyone else get 40,778? All right.
So we both then half.
Yeah, that is just pure coincidence. Yeah, sometimes the program will offer really formulaic problems. So just setting up the producer surplus, because this integral is even easier, it's going to be P star Q star minus the integral of the supply curve, which in this case, we already know P star Q star is 48,778 minus the integral from 0 to 841 of just 2 root x. But instead of writing root x, 2x to the 1/2. There. So we've been approaching this whole question about consumer surplus and producer surplus, which is based on the idea of a capitalistic society where you have supply and demand interacting with each other and finding equilibrium, which the market finds that equilibrium price. What did I do wrong, Josh?
The 2x to the 1/2 for the producer.
Yeah.
Be a negative one.
Well,
No.
the supply curve is just 2 root x. Okay, great. Well, but let's just pretend that we didn't live in a capitalistic society. What would the opposite of the capitalistic society be? I mean, maybe, yeah, I don't know about that. But who sets the price? If it's not the market that sets the price, who sets the price? If the government sets the price, right? Is that called a demand? What is that called?
Dictatorship.
Sure, dictatorship. Well, in any case, the government would set the price. Well, so let's just say the government sets the price. I mean, here we were saying that supply and demand sets the price here, and that's our P star, which is capitalism. But let's say that there was no capitalism. Who's going to set the price? The government. Well, so where is that going to be? It's either going to be higher or lower, right? It doesn't really matter what. But the point is that even if, so now this is my price star. So even if the government set the price instead of the market, couldn't we still imagine that there are people in society who they're like, hey, awesome, I only have to pay this much, but I would have been willing to pay more. So as far as I'm concerned, I still have extra money in my pocket. And there would still be businesses in that society who are like, oh, fantastic, I would have been willing to spend or charge much less, but I got to charge this much, so I still have money in my pocket too.
They just can't go past that.
Right, so I mean, whether the market sets the price or the government sets the price, aren't there still consumers who have money in their pocket that they're happy about and businesses that earn more money that they're happy about? So does this concept have anything to do with capitalism? Not really. Not really. No one could try to say, this is a benefit of capitalism. Because it would happen in any society, right?
Yeah.
Okay.
If you want to.
Right, and then the real fact is that no matter what price is set, you're still going to have people with money in their pocket, and still going to have businesses who made more than they thought, no matter what price you set. So this is very flexible in concept. This is a very flexible concept, isn't it? What does it really even tell us? I mean, it's just like, we're just making a comment that whatever you pay, there are going to be some people who are happy about it and some people who aren't. And we're just trying to attach a dollar value to it. Right? I'm not trying to disillusion you, like, this is worthless. I'm not trying to say that. I'm just saying this is a pretty flexible concept. Right?
Your point on Tuesday was that the equilibrium is not necessarily received.
Yeah, the equilibrium is not necessarily what the government would say. Yeah, because the government, our own government, already sets prices to be different things by subsidizing people. So even though the price is set by the market, the government comes in and subsidizes certain farmers and certain other businesses. So I mean, what are we even really talking about? I don't know, but I should just digress and let's just do the next problem. I'm just brainstorming with you folks, you know, thinking critically about this concept. Okay, that's funny. You could use the phrase "thinking critically" as a double entendre. Critical thinking means you're thinking carefully, but critical thinking also means you're being critical, right? Yeah. That's kind of fun. All right. Great. So the last problem that we'll do here is a different type of setup, but we're still computing the same thing. So let's read carefully what they give us. All they tell us is the demand function. They say, suppose the demand function for a particular product is given by that. So let's draw our graph. The demand function is linear. It has a y-intercept of 56.1, and it has a negative slope. I hope I've impressed upon you that it's okay to make kind of rough sketches. Better to make a rough sketch than no sketch, you know? And I think my graph is fantastic. It has the correct y-intercept, and it's negatively sloped. I mean, this is a great graph. Okay, so it says, find the consumer surplus corresponding to Q equals 800.
Essentially, this is
Yeah.
so that we just plug straight into you need to find what the piece is.
Well, that's an interesting point. Okay, so notice we're done with the instructions, right? What are we missing? Yeah, we don't have a supply curve. What would the supply curve have given us? Yes, a positive slope, and theoretically, it would give us, like, here's the point of intersection. I mean, we're kind of pretending, right? That this would correspond to what the supply curve would be, but we don't actually know what the supply curve is. But they are saying find the consumer surplus corresponding to 800, so this is kind of like our pretend supply curve. We don't actually know what it is. But whether we knew the pretend supply curve or not, could we calculate P star? Yeah, right? We just plug 800 into the demand function. So we'll do that real quick. So D of Q was negative 0.017 Q plus 56.1. So we plug in 800. Get something. I got 42.5. So there's 42.5 plus P star. Clearly, the rest of the information in the parenthetical should not be trusted because it says, do not round the results into the very end. That's good advice. At that point, round to the nearest tenth. That's fine. It may help you to sketch the demand curve, which crosses the horizontal at Q equals 3,300. It makes no sense. Because how does it cross the horizontal? And the horizontal down here, and Q is, oh yeah, that's just all wrong. That number 3,300 is wrong. In fact, what should that say? It should say 800. Right? Isn't that what it? No, that's still wrong. Oh, actually, maybe it's right after all. Where does the demand curve cross? Where would we find out where it touches down here? How would you find that out? How do you find out where that demand curve hits right here?
Set the equation equal to 0.
Exactly right, because this coordinate is some number, comma, 0, which means the output is 0. So we just set the function equal to 0. And if we set negative 0.017Q with 56.1 and set it equal to 0, well, gee golly, maybe that's where the 3,300 came from. Let's find out. It is? Okay, great. Well, in any case, I don't see why we would need to do that. But isn't that number still wrong? Oh, 56.1 divided by 0.017. Okay. All right, so apparently that is 3,300. I don't think we needed that, did we? It was just a matter of making a good graph. Yeah. Sometimes it's just nice to have all of your intercepts labeled. Okay. Well, folks, at this point, you would finish the problem as you would expect. You find C, consumer surplus, and producer surplus. Okay, so I think we're done with this problem as a group. Of course. Yes?
How will you find it if you don't have SQ?
How would you find what?
Like anything. Well, the producer surplus without SQ.
You're right that you couldn't find the producer surplus. You could not. But fortunately, this problem says find the consumer surplus. So we can still find the consumer surplus. Okay. Now notice that this problem brings up the conversation of let's just pretend that this is any number.
right? Like we're the government, we're gonna set the price. So, you know, we can kind of move that back and forth. And what does that do by moving it back and forth? Perhaps, as Henry wondered earlier, who's gonna have more? The consumers will have more money or the producers will have more money? And I guess the question that the government would ask, who do I want to be happy right now? Do I want the consumers feeling happy and optimistic, or do I want the businesses feeling happy and optimistic? Who's going to revolt against me first? And so then they could change the price of things depending on who they want to be happy, right? But wouldn't you want everybody to be happy? And so you should find the price that gives them both an equal amount. And if you find the right price that makes them both happy, wouldn't that be the price chosen by supply and demand of a capitalistic society? What did you say, America? Oh yeah. Okay. Okay, let's try the next couple problems. These last concepts, folks, here we are. This is the last concept, isn't it? Because we're about to take our chapter 3 test next week. And that means we're done. And then we'll study for our final exam. So this is our very last formula. Oh, sigh. This is our very last formula. It's an interesting one, too. So, what should we start reading first? Let's read the problem first. Number 8. Find the accumulated present value of an investment over an 8-year period if there's a continuous money flow of $11,000 per year and the interest rate is 1.2% compounded continuously. Wow, that's a long sentence with a lot of words, with a lot of ideas. So first of all, let's go back to accumulated present value. That means something very particular. So we're going to have to come back to talk about this. But let's just read on. What if we made an investment over an 8-year period? So first of all, we're investing over 8 years. So here's time 0, here's 8 years. And we're going to invest money. The money that's being invested, it's a continuous flow of money at $11,000 per year. So I'm going to make my x-axis much bigger. And I'm going to go to 1, 2, 3, 4, 5, 6, 7, 8. So that's after 1 year, 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 8 years. And what we're saying is that for whatever reason, however it is, you're putting money into the bank continuously at a rate of $11,000 per year. So if you start with no money in the bank, what? Yeah, you have a job. What you know for sure is that at the end of 1 year, how much money will be in the bank? Yeah. And how did the money go in? Well, it went in continuously. That means that it's not like you put in $1,000 a month, or it's not like you put in $500 a week. You turned on the money flow, and a stream of money water just started flowing into the bank continuously. The pennies are still discrete, but rather kind of like your bottom line digits of how much money you have in the bank. You'd have to imagine that it's just constantly updating itself. Like, can you imagine those little dials that turn, like on a slot machine or something else, or like on a gas tank? Well, old gas tanks. There used to just be dials of numbers. So you just have to imagine that money is constantly going into your bank account. All those wheels are constantly spinning, and the amount of money in your bank is going up and up and up over time. Not like tick, 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 but smoothly increasing. Okay? Once again, the bathtub analogy is a good one. It's not a drip of water every couple seconds. It's just a thin stream of water that's always filling the bathtub. So first of all, that's what a continuous money flow means. So a continuous money flow means that if all we did was just turn on a continuous money flow, then our graph would look like that. Where if you mark that off every year, you're counting up by 11,000 per year. So that your various amounts here, 11,000, 22,000, 33,000, 24,000, 55,000. I don't think I put my tick marks appropriately. To be 1, 2, 3, 4, 5, 6, 7, 8. Till we end up with $88,000. So that's what it would look like if you simply had a continuous money flow of 11,000 per year. That's what your bank account would look like. But there's something even better happening here, and that is you're actually earning interest on this. And the interest is actually being compounded continuously. So the bank now is also pouring money into your account with a continuous stream of money water. And that continuous income that you're earning from interest is happening at a rate of 1.2%. So now, here's what's really cool. You have to imagine that linear straight line. I know it's curvy, I'm sorry. That's a linear straight line representing your continuous money flow of 11,000 per year. That whole line is going to start being lifted because you're actually earning continuous interest, right? And the rate at which it's lifting is actually becoming steeper and steeper as time goes on because there's more money inside to get your interest on. So the blue line is my continuous income. The black line is with my continuous interest. All right. So that's completely ignoring the first few words where it says find the accumulated present value of an investment. We're ignoring those first few words and just saying, hey, if over the next 8 years you have a continuous money flow of 11,000 per year, and that money flow is earning an interest rate of 1.2% compounded continuously, how much money do I end up with at the end? How much money do I end up with at the end? So first and foremost, how much money would you have at the end if you didn't earn any interest at all? You did $80,000, right? But since you're earning interest on that money at all time, then it's actually going to be more than 88,000, right? Yeah, 88,000. So first of all, how would we compute that? Just that interest alone? That's a pretty good question. Because normally, when we've calculated interest, continuous interest, it's just P e to the RT. So it'd be one thing if I said, hey, I have $11,000 in the bank. How much continuous interest would I have at the end of 1 year? But we don't have $11,000 in the bank. In fact, at every moment in time, we have a different dollar amount in the bank because the money in the bank is constantly going up. So the money that you're computing interest on is constantly changing. So we can't just use this formula because this assumes a fixed principal and our principal is constantly changing. So at the very least, can we agree that this is a little bit of a tricky problem? And you might even wonder, who has a continuous money flow? What is that? I've never had one of them. What? Yeah, maybe Bill Gates or somebody else. All right. So now though, now that we have our eye on the main goal, which is to calculate this dollar amount right here, the question, find the accumulated present value, circle that phrase, and we're going to rewrite it right now. The accumulated present value would be what lump sum would I need to invest at time 0? So a lump sum amount to end up with the same ending total. So, give me a second to finish writing that. What lump sum would I need to invest at time 0 to end up with the same ending total? So now, in a completely alternate reality, like instead of having $11,000 streaming in all year long for 8 years, what if I just had a lump sum dollar amount that just boom, my grandma or somebody just give me a lump sum, let's just say 70,000 bucks, and all I do is I just throw it in the bank and I just wait. But I want it to hit that same target value. Okay? What lump sum would that have to be so that it's just a fixed lump sum and it's going to grow over 8 years at the same 1%, 1.2%? So what would the lump sum have to be to yield the same final dollar amount as my continuous money flow, which is also earning interest? Okay. Well, if the question makes sense, again, you might be saying, in what reality does this happen? This is not a problem I have in my life, to figure this out.
Nevertheless, that's what the question is asking. So now let's read our box. Continuous income stream. Suppose money can earn interest at an annual interest rate of R compounded continuously. That's our 1.2%. Let f of t be a continuous income function that applies between year 0 and year t. So our f of t right now, our f of t is the constant 11,000. We're earning $11,000 per year. That's your continuous income function. No, because every year you earn 11,000. This year I learned 11,000. This year I earned 11,000 more. This year I earned 11,000 more. This year I earned 11,000 more. If you wrote 11,000 T, that'd be more exciting. I would like that. But that would mean that during the first year I earned 11,000. But in the second year I earned 22,000. That means earned. Okay. So now if that's your first year, that's your second year. Now I have 33,000 in only 2 years. This would mean in the third year I earned 33. That doesn't mean that by the end of the third year you have 33,000. That means during year 3 you earned 33.
Because it's not squared, but it's still not clear.
Yeah, it's just gone up. Like that. The weird thing is though that that's representing how much income you got that year. That is, see, these are two very different functions. Like, look at this point right here. That point for us means that by the end of the fourth year, I have $44,000. The function you're talking about, Josh, means that in the fourth year, I earned $44,000. Well, then I would have to go back and actually add all those up. Okay. So yeah, it's just 11,000. It's a good question, though. Okay. Then the present value of that income stream is given by this function. Okay. Let's all write that down in our own handwriting. So the present value, which means lump sum now. The amount of money that you'd have to have right now is a lump sum instead of the continuous money flow. Then that present value is given by the integral from 0 to t of f of t times e to the negative rt dt. And then they say, once you know that lump sum, you could still plug it into your normal PE to the RT function to compute how much it'll be worth later on. As a present value. Okay, so what we're about to do is compute, instead of this crazy idea of a continuous money flow, what if I just had a lump sum of money now and I just put it in the bank and I just waited this? Okay, so that's the trade-off. You either get a teeny trickle of water all the time for the next 8 years, or I just give you a big lump sum right now. Okay, so that's your trade-off. Okay, let's go ahead and do the integral then. So in this case, our integral will be from 0 to 8 of 11,000 e to the negative, what's 1.2%? 0.012 t ut. About distinguishing between a continuous money flow over the next 8 years versus a lump sum at the beginning of the 8 years, that integral is pretty easy. Is that integral pretty easy? Because remember, what's the integral of e to the n x? It's just 1 over n e to the n x. So all we have to do this integral is we're just going to take our 11,000 and divide it by negative 0.012. So let's do our integral. So it's going to be 11,000 over negative 0.012 e to the negative 0.012 from, this is a 2 there, 0 to 8. Now, you might be looking at this thinking, uh-oh, something's wrong. Because what's 11,000 divided by negative 0.012? Negative something. So does that mean that my present value, my lump sum that I need is negative? That'd be weird. Yeah, well, good point. The problem's not done yet, right? You can't always just look at intermediary steps and be like guessing what the answer is going to be. We still have to plug in 8 and 0. And look, when we plug in 0, is it going to equal 0?
Yeah, no, it's gonna be that times 0, which is 0, e to the 0 is 1. So we're actually gonna be computing e to the something minus 1. And that could actually turn that quantity negative, and then negative times negative would be positive again.
Wouldn't it be this one because it's minus and then that zero is there, it's minus.
I'm not sure. Let's do it. Hold on to your question and just watch. So I'm gonna go ahead and leave that outside. Like, coefficients we're allowed to leave outside. I'm gonna divide that out and get rid of it. So it's really negative 916,666.6 repeating. Outside of e to the negative 0.012 times 8 minus e to the 0. Remember what I just did? So I divided my 11,000 by negative 0.012, and then I plugged in 8 and I plugged in 0. Now this part I can just plug into my calculator. So I have negative 916,666 and 6 repeating times the that's negative 0.1476561. And that will end up giving me a positive. $135,534. Yes, and it is positive. Josh, did that answer your question or no?
My question does not.
Oh, okay. Because this ended up being 0.9 minus 1. So that in fact was negative. Well, 0.908.
If the second term is larger, then it becomes positive. It's not a term.
Yeah. I've done something wrong here. I did do something wrong. My numbers are all wrong, folks. I
83,000.
yeah. I didn't do that correctly. E to the negative 1, 2. Okay. There we go, minus 1. So that's actually negative 0.09153. Oh, that's great. Because boy, my number seemed very big at the end. And you know what I did? I ended up doing this computation in 2 different ways. Using the entry trick and not using the entry trick, and I saw that there was a difference, and then that pointed out to me that I did it wrong. So now that times 96. Okay, that's much better. 83,907 and 99 cents. Okay, so what is that 83,000? That's the lump sum. So now consider what we're saying here. We're saying that either, okay, so either 83,907.99 now and let it earn interest, or 11,000 per year for 8 years while letting it earn interest. And those two choices are identical. Those two choices are identical. It might be tough to convince someone of that. Because over here, you're getting 88,000 for sure, plus interest. Whereas over here, somebody's only giving you 83,000. So a lot of people who might, I use the word naive in a nice way. Being naive doesn't mean you're an idiot. Being naive just means you don't know the math. So somebody who's naive would say, well, no, I'm going to do this way. It's 88,000 plus some interest. This is just 83,000. But the fact is the 83,000 earns interest for a very long time. Whereas when you only get the 11,000 per year, in the beginning, you have a very small principal earning interest. So you're not earning much interest. Whereas this person has $83,000 earning way more interest. So, but they balance each other out in the long term. Okay, let's finish the problem and then we'll just be done for here. You'll notice that we still haven't figured out how much money this first person ended up with, right? this first person ended up with 88,000 plus interest, but how much interest? And I told you that's challenging because that first person, it's not a fixed principal, the principal's changing over time, so we couldn't use this formula. But now that we have a lump sum that's guaranteed to be equal to the same ending amount, I can now just take my lump sum, which is 83,907, and simply use A equals PE to the RT. So now, the amount of money that I'll have at the end, that both accounts are going to have at the end, is 83,907.99 e to the positive 0.012 times 8. So this is kind of like figuring out how much money that 11,000 continuous person is making by going the back way of first computing a lump sum that's equivalent to it, and then computing how much interest the lump sum person is getting. So what is it? 83,907. 2 times 8. They're both going to end up with 92,362.48. They're both going to end up with that much. So going back to my sentence, either 83,000 now or 11,000 continuous per year, both earn 92,362.48 cents. And what's so interesting about all the math that we did is that we never actually did compute how much the first person got. There was no formula that we were able to use to actually compute how much interest you get from a continuous income flow. What we had to do was actually compute an equivalent amount of money as a lump sum at the beginning, find that interest, and then we were able to say, oh, but those two things should be equal. So that's how much the 11,000 person is going to earn as well. Henry?
But it's kind of saying that the first person had to put 88,000 in, and the second person got to like spend $4,000 on whatever they want. Both have the same money. That's the thing, right? So if you have the 83,000 up front,
Yeah.
then you could spend the 4,000 on whatever you want. They're both their banks say the same thing after 8 years.
Oh, so you're saying like, I'm going to give you $88,000. Okay, so everybody in the room, you get $88,000. And either you're going to put the $88,000 into your bank at $11,000 per year, and you'll end up with $92,000. Or you take your $88,000, immediately go blow 4,100 of it, and just invest $83,000, and you'll end up with the same amount as the other person. That is absolutely correct, Henry. Yeah, boy, that's really weird. Now more than ever, I want the lump sum so I can go blow $4,000 right now, and I'll still end up with the same amount of money as the other person. Yeah, very interesting. I've never thought of it that way. Yeah. Okay. Now, what do you think, folks? Should Henry be put in charge of a business or not? I mean, that's some shrewd thinking. Maybe so. All right, folks, we didn't finish that section, but that's okay because on our calendar, we still have next week on Tuesday to finish 3-7. So we'll come back and finish that, look at your practice test. Did everyone get a practice test? I didn't really hear anybody say anything, but I have extra practice tests. The extra practice tests are right here if anybody needs one. So please come, make sure you get it.